Most of you are likely quite familiar with the Canadian prairies, but what comes to mind when you think of them? Is it endless flat fields of canola and wheat crops and great photo ops? While this is fairly accurate, the prairies are actually much more diverse than that. Spanning the provinces of Alberta, Saskatchewan, Manitoba, and lands of Treaties 1, 2, 4, 6, and 7, this large region encompasses a variety of physical features. These landscape characteristics create hydraulic variability throughout the region. To help understand this, the Prairie Water Research Team divided this area into 7 types of watersheds based on geological, topographical, and land cover data, with each expected to respond in a coherent hydrological manner. So why is this useful? Well, since the prairies are largely dominated by agricultural activity, changes in land use or management such as wetland drainage or tillage practice are expected to influence the local hydrology. Additionally, the prairies are not exempt from the impacts of climate change. In fact, since the region is semi-arid and experiences the seasonality of both cold and hot conditions, it is extremely susceptible to warming temperatures and shifts in precipitation. Therefore, watershed classification allows an efficient way to increase the predictability of hydrological changes under these environmental stressors. 2 of these classes, the Pothole Glaciolacustran, PGL, and Pothole Till, PHT, cover a large extent of the prairies and also exhibit relatively similar characteristics. Therefore, my project was to compare the responses of these 2 classes under historical and climate change influence to find dominant differences between them. In order to do so, I utilized the cold region's hydrological model to run virtual basins of the PHT and PGL classes. This model was driven by Saskatoon meteorological data from 1960 to 2006, and climate change was simulated with increases in temperature and precipitation. Various hydrological responses were output from the model, including snow water equivalent evapotranspiration, soil moisture, depressional storage, and storage overflow. Through this analysis, I determined that the PGL class exhibited greater annual stream flow than the PHT class by 22%. This was found to be largely attributed to the basin's differing characteristics of superficial geology, in which PHT's more hummocky terrain created deeper topographical depressions which had a greater capacity to store water, whereas the flatter terrain in PGL results in shallower depressions and routed more water to stream flow. This suggests that under differing land use management like wetland drainage, the noted discrepancies between these classes may further diverge. Under climate change, the classes were projected to respond in a similar manner. Both were expected to have reduced snowpack and stream flow under warmer climates, and that this could potentially be offset by increases in precipitation. Additionally, both classes were modeled to reach peak stream flow earlier in the year. Together, this showcases that the hydraulic response of both of these widespread watershed classes is largely influenced by wetland storage capacity and the dynamics of snowmelt runoff. These results provide insight into how these 2 classes will differ in responses to changing land use and environmental conditions for the continued work of the Prairie Water Research Team. Thank you for listening.